to talk about the research and the projects. Okay. So about MARVECX Aerospace is a forward-looking African aerospace company committed to advancing aerospace design, research, and education with a deep focus on sustainability and innovation. The company bridges aerospace engineering, environmental responsibility, and technological development, ensuring that innovation contributes meaningfully to life on Earth and beyond. MARVECX operates through three major sectors, and that is education sector, research sector, design and manufacturing sector, which Francis will come speak more about it. Then we have mission, vision, and core values. The mission is to develop world-class aerospace technologies, promote research for sustainable and multiplanetary future, and empower individuals globally through education, collaboration, and innovation. Our vision is to position Africa as a major player in global aerospace and technological advancement while leading the transition toward a sustainable and spacefaring civilization. Core values are innovation, excellence, collaboration, sustainability, empowerment. The flagship program, we have International Space Technology Convention, MARVECX annual global platform connecting scientists, engineers, and innovators to discuss advancements in aerospace technology and sustainable innovation. Impacts and achievements, hosted ICTC 2023 and 2024, empowered youth through STEM outreach and mentorship, fostered aerospace education and global collaboration across Africa, promoted sustainable development within aerospace and energy sectors. Housekeeping rules, drum rolls. Keep your mic muted. Q&A timing will take place at the end of each segment. Submit questions. Please drop your questions in the comment or chat section throughout the section. And session structure, each panel or session has 25 minutes. This is to the speakers, followed by 5 minutes of Q&A. The questions, quality, keep your questions clear and concise. All right. Now, I'm going to just go through the speakers that we have published, and then again, I will introduce them each by saying their bio, but before that, we'll have Francis to come for research and the projects in the digging dive there. All right, we have Dr. Taofiq Amoloye, the coordinator in Aeronautical Engineering in Kwara State University, Nigeria, expertise in aerodynamics, fluid dynamics, and astrodynamics. Then next, we're going to have Neal S. Lachman, founding CEO of Titan Space Industries USA, expertise in CIS lunar economy, STHL, space planes. We have Rama Murali, head of AEIV, Space Inventor, AOS. Denmark expertise, satellite integration, mission qualification. Then we have a short break. And then we're going to have Dr. Sheet Jamal, director of Brahman Lab, University of South Alabama, USA, expertise in system engineering, explainable AI, Mars mission. Then we have Merrick, CEO and co-founder, the Radiation Team USA, expertise in radiation engineering, space systems resilience. Then we have Dr. Srimathy Kesan, founder and CEO, Space Kidz India, expertise, students, satellites, and women in STEM. Now, I'm going to welcome Francis, who is the acting research lead for MARVECX. Francis, are you there?
I'm with you, Kristen. Yeah, please confirm if you can hear me.
Yes.
All right. So thank you so much, Kristen, for that welcoming and also running us through um, MARVECX and what we do precisely. Please confirm if you can see my screen.
Yes, Francis, I can see your screen.
All right. All right. So good everyone, morning, afternoon, evening, right? Irrespective of wherever you join us from the world. And welcome to day 2. And we are so glad and excited to have you here. So before today's section actually start on, we would love to run you through what we're actually doing here at MARVECX and trying to bridge the gap between project, research, and education. So this is just we trying to allow you to meet us, who we are, and especially what we're trying to achieve in that aspect of our research, education, and our project. So I'll be presenting to you MARVECX strategic vision for this particular goal, right? So our mandate is simple, right? As this year ISTC team it's called Emergence, right? And so our aim is also to also follow suit with our team and also be in action with this. So that means we're actually trying as much as possible to advance innovation, sustainability, and space exploration. And this actually translates into we in terms of turning our research into tangible space technology prototypes and also focusing in sustainability and ensuring that they're actually efficient, viable, and responsible product development. And we go ahead as possible and actually, exploring different aspects as we're actually trying to prepare MARVECX to actively contribute to the global space endeavor in the year 2026. So the 3 pillars to allow us to achieve all of these things is through our project approach, our research approach, and also our education approach. So the very first pillar, project. So this is more about we trying to create the prototyping of whatever stuff we're about to engineer. So the mission is very simple. The mission is to be able to be the execution arm responsible to turning research, right, into physical space assets. So what is our immediate goal? What we are trying to actually achieve at the nearest possible time is to kickstart prototype building in year 2026. And this actually looking at building like small scale satellites, CubeSats, and suborbital rockets, right? So the method of this particular development is more like agile development and lean engineering principles. For those of us not really in the engineering space, so it's more like we actually dividing our works to little chunks and to be able to follow up these particular processes to achieve our goal at the shortest minimal time. So the impact we're expecting to have is to be able to establish MARVECX as a technological developer, not just a host, as you know us to be. Our second pillar, which is actually research, is for us to facilitate existence. And this actually is more like providing technical validation and risk mitigation for the project department. So our key areas enable to achieve our small satellite building, our rocket prototype, is to be able to look at radiation effects, thermal management, orbital mechanics, and most importantly, AI integration. We all know that we are in the world of AI, and before we know it now, we are going to be in the space of powerful AI. So our external focus is actually advancing global space knowledge, which is what we're actually doing through ISTC. And this is actually the 3rd edition of ISTC. So this has actually been our culture, from time past since 2023 up to date. And so we also have this particular aim of having publication goals, right? To be able to ensure that we will be actually accepting papers, right, for subsequent conferences of ISTC that will actually be published in top journals, right? Most especially Scopus Index. Now, education. This is about we building capacity. Our mission is to be able to inspire, train the next generation of space engineers and scientists, right? And this is actually through the ISTC convention, specialized webinars and workshops, right? And most importantly, we have a section called the CI show, which is a core educational component. providing a global stage for participants to present their ideas, innovations, demos, or whatsoever. And I'm glad to announce to you that we'll be having the very first session of CI show this year. And that show will be coming up on Saturday. So I will expect each and every one of you to look towards it and come and see what we have for you, our innovators in town, and actually what they have to present for you this Saturday. Now, so the output of this particular project is to be able to create a pipeline for trained talent to feed directly into the MARVECX project. So where's the synergy here? Right. So the MARVECX flywheel. So this particular three departments is more like form a continuous self-reinforcing loop, right? That means that the educations, right, provide trained talents and knowledge base. The research is to validate our technical feasibilities and optimization. The project is to be able to validate and to build our prototypes, right? And this will actually accelerate our goals in having functional prototypes in the year 2026. So what's our call to action, right? Where do we need you and where do you come in? So this is where we actually need each and every one of you. So we're inviting rigorous original research submission from the ISTC community. So starting from next year, what I said, we'll be rolling out publications to be able to partner with journals, to be able to have our research out there. So that when you actually come for a convention like this, you also have the benefit of also presenting your papers and actually be published in top Scopus journals. So after this particular convention, you'll be communicated with on signing our submission window. And our area of immediate interest is small satellite building, like I said earlier, CubeSat, rocketry, right, and cost optimization, novel propellant propulsion system for small launch vehicles, AI machine learning integrations, satellite operation, space medicine, and health risk mitigation, right? So what are our key deliverables? What is our focus for the year 2026? So for projects, right, we want to be able to initial functional satellites and rocket prototypes ready for testing. For research, by your help and also by our help, to be able to successfully submit and publish high quality index papers. In terms of education, to be able to train talent pool ready to transmit into the project department. Overall, MARVECX is transforming from a conventional host to a technology builder, right? So thank you so much. So let's build a future together. And you can contact us at marvexspace@gmail.com in case you have any question. So I think that is where I'm actually going to end my presentation for today. Thank you so much. Over to you, Kristen.
Well done. Thank you so much, Francis. That was so informative. Hope everyone has heard. And actually now, if I start asking about what is MARVECX, anyone can just tell me. Now, the moment has come. Let's go to our speakers, and I'm going to share my screen again. Can you all see my screen? Hello?
Yes, we can. Loud and clear.
Okay. Thank you for replying. We're going to start with Dr. Taofiq Amoloye. So sorry if I'm pronouncing it wrong. So who is Dr. Taofiq? He's a coordinator department of Aeronautical and Astronautical Engineering, Kwara State University, Malete in Nigeria. He's from Nigeria, as I said. He has a Bachelor of Science of Aerospace Engineering, that is in 2009, KNUST in Ghana. Master's in Aerospace Dynamics, that is 2011, Cranfield Uni, UK, and 2017, and PhD in 2020 in Aerospace Engineering from Georgia Tech, Atlanta. He's the current coordinator of the Aeronautical and Astronautical Engineering Department of Kwara State University, Malete in Nigeria. His research interests include aerodynamics, fluid dynamics, turbulence, and astrodynamics. Mr. Dr. Taofiq, You're welcome. Please,
Thank
you
you
can
very
now
much.
speak. You're welcome.
I'm going to try to share my presentation now.
Okay.
I hope you can see my screen.
Yes, Doc, we can see your screen.
Okay, thank you so much. So,
Yes, I can see your screen.
okay, thank you so much. So I'm Dr. Taofiq Amoloye, and the topic of my presentation is emergence in the education system in Nigeria and West Africa at large, a focus on aerospace engineering. In this presentation, I'll be discussing the current state of aerospace education across the continent and in the West Africa sub-region. And then I will discuss some of the challenges so far and also touch on some of the opportunities that are there. Then I'll speak on some of the innovations and particularly on the development of refined potential flow theory. And then I'll draw some conclusions. The MC has done well to say much about me, so I'll go ahead to the presentation. Presently, there are 7 countries in Africa with aerospace engineering in their universities, and these are Egypt, Ghana, Kenya, Morocco, Nigeria, South Africa, and Sudan. In terms of the geographical spread, there's somewhat of an even distribution with Egypt and Morocco in the northern part of Africa, Sudan and Kenya in the eastern part of Africa, South Africa in the southern part of Africa, and of course Nigeria and Ghana in the western part of Africa. There is currently a single university in Ghana offering aerospace engineering, and that's Kwara University of Science and Technology, my alma mater. In Nigeria, there are 9 universities. Presently, 9 universities offering aerospace engineering. The first one to start aerospace engineering is Kwara State University, where I'm the current coordinator, and the program started in 2010. The latest addition to the list is Isaac Balami University of Aeronautics and Management in Lagos State, which kickstarted its program this year. Out of all these universities, 2 of them are privately funded. That is Afe Babalola University and Isaac Balami University of Aeronautics and Management in Lagos State. 2 of these universities also currently offer postgraduate degrees in aerospace engineering. That is Air Force Institute of Technology in Kaduna and the Institute of Space Science and Engineering, which is an affiliate of the Pan-African University, African University of Science and Technology in Abuja. Over the past 15 years, WASU Aeroastro has been contributing to the global pool of expertise in aerospace engineering, and some of the notable alumni are Habibullah Abukadri, who bagged his PhD in 2023 in the US. There's also Habib Babatunde Idris and Emmanuel Osayu Linfu, who are presently enrolled in PhD programs also in the US. And of course, there is the CEO and founder of MARVECX, Marvelous Ayinde, who is doing a very good job with this convention. There's been floating the program aerospace engineering has not been without its own challenges. One of the main challenges is the inadequate funding for advanced aerospace engineering research and development. And there's also a lot of difficulty in recruiting and retaining adequate number of staff with requisite expertise and training. There's also the difficulty in establishing collaboration with relevant industries. However, there are also opportunities in the very large pool of passionate and talented young minds that are present. and on the merits of local problems that require aerospace-related solutions. Some of these problems are food security, socioeconomic insecurity, as Nigeria is currently facing, and of course, the sub-region at large. Where talents meet problems, there are bound to be innovations, and of course, there can be some economic benefits from those innovations. Some of the challenges have also been given the impetus for my inquiry into a classical fluid dynamics problem, that is the viscous flow on a circular cylinder. Cylinder flows have geometric simplicity but a very complex flow pattern. I found this video online which does a good job in explaining the flow over a circular cylinder. So let's just watch this. Please let me know if the audio is good. Okay.
How does fluid flow around a cylinder? A simple enough question, but one that cannot be answered without some extra information. The flow profile depends on the size of the cylinder, on the inflow velocity, and on the thickness or viscosity of the fluid. In fact, these three properties combine to form the Reynolds number, and it is only this Reynolds number that then dictates the behavior of
And of course, the flow is also dependent on time.
flow. For a very small Reynolds number, the flow remains fully attached, and in the limit to zero, the profile becomes fully symmetric. Past the Reynolds number of around 4, the flow detaches from the back of the cylinder, and a small separation bubble is formed. The size of the separation bubble increases with the Reynolds number. Take a look at the more detailed information on the web post of Figure 42 on albumofcfm.com for the precise dependency of the size of the separation bubble on the Reynolds number. There you will also find how all the simulation results shown in this video were obtained. The separation bubble keeps on growing until it is larger than the diameter of the cylinder itself. Of course, it cannot grow indefinitely, and at some point the system becomes unstable. Past the Reynolds number of 46, vortex shedding begins to occur. The separation bubbles no longer stick to the back of the cylinder, but are instead dragged into the surrounding fluid. When we zoom out, we see that these isolated vortices are transported far beyond the cylinder. This resulting pattern is called the von-Karman vortex rate, a well-known phenomenon that is also observed in clouds passing mountains or ocean currents around islands. At around a Reynolds number of 1,000, the flow loses all stability and the wake becomes turbulent.
Yeah, we see that the classical potential flow theory, which is juxtaposed with the video that just played, does not offer the avenue to have the plethora of flow patterns that can occur in the flow over the circular cylinder. So the question is, can these complexities be modeled analytically in potential flow theory? Cylindrical structures are very common in engineering applications. Utility poles, girders, chimneys usually have cylindrical cross section. Even some tree trunks also have cylindrical cross sections. Of particular interest to this research are helicopter tethered loads, such as depicted in Figure 2 and in Figure 3, an engine canister there. That can be subjected to complex dynamic responses due to the unsteady interplay of the aerodynamics and the dynamics of the system of feeder cables and the helicopter. Even for the most seasoned pilots, this can pose a very great challenge. However, for stability analysis, flight certification, and pilot training, the cost of experimentation and CFD analysis of this configuration, CFD meaning computational fluid dynamics analysis of these configurations, can be prohibited. Therefore, reduced other models of such configurations that take in the aerodynamics model of the fitted loads are employed for flight simulations for pilot training. but there's a dearth of realistic and analytical models of final cylinder flows that because of the Navier-Stokes problem. Classical potential flow theory, which can provide an avenue to develop such models, has the extant gaps in its predictions that significantly preclude it from usage in engineering applications. Therefore, there's a need to refine it. The governing equations and boundary conditions of the flow are here. The equation obeys the principle of conservation. The flow, that is, obeys the principle of conservation of mass, and therefore the continuity equation in equation 1 governs it. Of course, the assumption here is that the flow is incompressible. If there is a further assumption of irrotationality, the divergence of the equation, continuity equation saying divergence of velocity equals to 0, also obeys the Laplace equation. The conservation of momentum is enshrined in the Navier-Stokes equation presented in equation 2. In these equations, the variables have their usual meanings. The boundary condition for the flow is the free stream approaches the flow approaches the free stream value far away from the cylinder, and also the flow adheres to the cylinder surface, that is the no-slip condition on the cylinder surface. Here, table 1 summarizes the areas where classical potential flow theory currently matches experimentally observed flows. We see that both classical potential flow theory and the experimental flows obey the continuity equation. They also satisfy the Navier-Stokes equation. They are bounded at infinity. The streamlines are smooth, continuous, and they are also physical. However, classical potential flow theory does not obey the no-slip condition. There is no Reynolds number dependence. You can't have vorticity in the classical potential flow theory. There are no boundary layers, wakes, vortex shedding, unsteadiness, and also the classical potential flow theory usually gives two-dimensional solutions. These are all contrary to observations of actual flow. My work on the refinement of the theory is published in Physical Scripter, and it's the paper I highlighted here. The focus was on modeling the wake of the impossibly started circular cylinder flow. Matiswaran and Miller also recently worked on improving classical potential flow theory, but their focus was on surface quantities as well as steady flow. RPT, that is refined potential flow theory, employs a solution to the Laplace's equation, the general solution, that is equation 3, to construct a viscous stream function as in equation 4, which is a superposition of 5 constituent terms. The details of all these derivations can be found in the paper. The results will just be discussed here for brevity. Looking at the cylinder flow, the impossibly started cylinder flow, it involves a complex interaction between the boundary layer, the free shear layer, and the wake. The boundary layer, the schematic of the boundary layer is presented here, where the flow velocity goes from being 0 at the surface to its free stream value at infinity. So for the classical potential flow theory, to model the cylinder flow, we just have the uniform flow superposed on the doublet flow to have this. For the refinement of classical potential flow theory, what was done is to introduce some singularities on the surface of the cylinder. Singularities meaning elementary flows such as sources, sinks, and vortices. All of these singularities are allowed to be concentric at every point on the cylinder surface, and then the equation for the entire flow is assumed to be a subset of the general solution to the Laplace's equation that was discussed in the previous slide. And so now a representation of the ensuing flow is presented in equation 5. Here gives the classical potential flow theory, and here gives the what refined potential flow theory brings to the table. The paper comprises of the procedure to have to define this term based on physical deductions and observations of experimental flow. So RPT then defines an unsteady viscous planar stream function given by equation 6. The contour of this equation 6 is presented in figure 4 here for Reynolds number 26, where we can see the gradual growth of the separation bubble with non-dimensional time. Since, like I said, this unsteady stream function is a planar solution, that is, it's just on a two-dimensional plane, there needs to be some three-dimensional consideration because the actual cylinder flow is three-dimensional. So in refined potential flow theory, there are two coincident coordinate systems. First is the geometric spherical coordinate system with a varying circumferential axis, described in equation 7 here, and it's just the normal coordinate system that one would define for a three-dimensional object. And then the second one is a perpetually two-dimensional wind coordinate with constant circumferential coordinate axis at pi/2, and that's here in figure 5, which shows the geometric relationship between the geometric and the wind axis, coordinate axis. Here, the wind axis that I'm talking about is the one in purple, and the circumferential coordinate axis of the geometric coordinate system is the one in green that is allowed to vary. So the solution, the planar solution that was discussed in the previous slide, is defined on the purple plane, but it is allowed to also vary for, that is for each and every phi, the green coordinates, there is a planar solution that is defined on the wind axis that follows it. So doing that, we also define the body axis, the body coordinate, that is with equation 9, and then to conserve momentum, to conserve mass and momentum, we look at these equations here. Since we are talking about a stream function, the divergence of the velocity will always be equal to 0. So for every one of those wind axes, this equation holds true. That means the solution, the foregoing solution, conserves mass. And to conserve momentum, the theta axis of the solution is transformed from the usual definition here to this definition, that is theta equals arctan x over y instead of arctan y over x. Doing this transforms the viscous, the unsteady two-dimensional planar stream function to a new function here, kappa tilde, which I named the Poisson function. Figure 6 here shows the geometric relationship between the stream function, that is the viscous stream function, and the new function that was derived from it. So because the viscous stream function is defined on the principal Cartesian coordinate axis, about which the Botizzi vector is identically equal to 0, it means that the derived function, that is the Poisson function, is a quasi-rotational stream function from which the velocity field is obtained as follows. In the polar coordinate system, cylindrical polar coordinate system, that is, to get the velocity, one would have to take the curl of the vector of Poisson stream function. But in the Cartesian coordinate system, one just has to do the gradient of the Poisson function. And doing that ensures that we can then couch the momentum equation in terms of the Poisson function from its definition, from the way it's defined with the stream function. We can couch it in the Poisson function, and then we can obtain an expression for the pressure field as in equation 12. So to verify and validate the results of the refined potential flow theory, here is a video that shows some experimental flow at Reynolds number around 120, and the refined potential flow theory flow at similar Reynolds number 140 first in a stationary frame of reference and then in a moving frame of reference. We can try to see the evolution of the wake, and also in this flow, the flow direction, the overall flow direction is from top to down, or we can see that in the wake there is a backflow in the experiment, and that backflow has also been captured in refined potential flow theory. Here, I'll try to play the video again. Here, and if we go to the end of the video here, we see the comparison at Reynolds number 3900, where the flow patterns these are instantaneous flow patterns, and they seem to agree quite much. Here, video 3 gives an animation of the RPT solution at 3900, and video 4 gives the actual flow pattern. Figure 7 here presents the power spectral density plot at results from RPT for 3 different Reynolds number: A Reynolds number 56, B Reynolds number 3900, and C Reynolds number 9500. There's a sharp peak at the structural frequency, which is characteristic of a laminar wake. That, of course, is expected at RE56. At RE3900, the sharp peak disappears, and there's a transfer of energy to substructural frequency, and the harmonics of this structural frequency start showing up. This is also something that is expected from experimental observations, and the same also goes for the case of the RE9500. The case here at RE3900 is particularly interesting when we look at table 2, which compares the prediction of the structural number for RPT as against experimental results and results of CFD with different turbulence models. We can see that the prediction 0.209 is well within the error bound of the experiment, and also matches excellently with the prediction of CFD with using the THRLES method.
Dr. Taofiq, you have 2 minutes left.
Okay, I'll quickly I'll round up now. When we also look at the one-dimensional energy spectrum of the wake, we compare the experimental results to RPT results. We also see that RPT is able to capture the slope of the velocity spectra, which means RPT is able to capture the turbulence in the wake. Further downstream, we have the same. Here, video 6 shows here shows the flow over an island. I'm just going to try to play the video. So it's the flow over an island as captured by a satellite. So this is an island, that is the flow, and that's the wake showing the on camera flow pattern. Here, to model the flow, we use RPT to define the flow over a sphere, and then put that solution on a topocentric horizon coordinate system in figure 10 to have this kind of flow pattern here in the video. This kind of solution will have implication for atmospheric turbulence modeling for launch vehicle designs, and they can also have implication for re-entry vehicle aerodynamics. So in conclusion, the university education in aerospace engineering started off in 2004 at Kwara University of Science and Technology in Ghana. That is university education in West Africa. And Kwara became the first Nigerian university to offer the degree in 2004. Presently, there are 10 universities in West Africa offering aerospace engineering, one in Ghana and 9 in Nigeria. There are engineering needs for the refinement of classical potential flow theory. Classical potential flow, refined potential flow theory closes the gap between theory and experiments, as in table 3 here. There are excellent predictions of brake characteristics as function of Reynolds number and Stroll number, and the inertial range of turbulence are well predicted. RPT can thus be applied in reduced order models of engineering applications that employ cylindrical structures. These are video resources on RPT, and these are the references in the presentation. Number 3 here is the reference to the paper on RPT. Thank you very much.
Thank you so much. Thank you so much, Doctor. You can see some reactions. You can see how well your presentation was, and you're smiling. I'm so happy about that. There is someone who had a question, by the way.
Okay.
In the chat.
Please go
He or she is saying, do you currently have contact with these universities? Do they have any needs for satellite material verification or spacecraft carrying cargo? We can discuss this together.
Yes, definitely. We are open to any kind of collaboration. Please reach out to me on LinkedIn. Yes, my email is displayed on the slides. You can also reach out to me by email.
Okay.
Yeah.
Oh,
thank you.
Oh, it's a he. He has replied.
Thank you so much.
Anyone who has a question, please, you can raise your hand, or you can mute. I mean, you can unmute, and then you can ask Dr. Taofiq. No one has a question. Oh my God. All right, let's say you're going to keep your questions. Right now, we'll go to Dr. I'm going to present here. Dr. Srimathy. She's going to present next. I'm going to read her bio. Let me share my screen. Thank you, Dr. Taofiq. I hope people will keep writing the questions on the chat, and then we will come back when you. So if anyone has a question for Dr. Taofiq, please, after you've written your question in the chat, please tag so that I can know that question is specifically for Dr. Taofiq. Thank you, Dr. Taofiq.
Thank you so much.
You're welcome. Now, I'm going to read my bio. I mean the bio for the next speaker.
And please, people can also reach out with their questions to me via email or on LinkedIn if they don't want to present them now.
Yeah, sure. Please reach out to Dr. Taofiq or Father. Okay.
Thank you.
Now, the next speaker is Dr. Srimathy Kesan, and she's the founder and CEO of Space Kidz India, an award-winning aerospace organization focused on pioneering student-led satellite missions. She holds the distinction of being the only woman founder in the world to have built and launched 27 space missions. Impressive. These historic missions include CalMAST, which was the world's smallest and lightest satellite launched by NASA, and Azadi-Sat, an all-women satellite used by 750 rural girls across India and launched by ISRO. She is the only Indian conferred ambassadorial status to NASA, ESA, and GCTC Moscow. A staunch advocate for women in STEM, Dr. Kesan has inspired thousands of young minds through international collaborations and hands-on space training programs. Wow. Dr. Srimathy, I hope you're there.
Yes, my dear. Thank you. Thank you so much. Well, if it is okay, I will just put off my video because I've just boarded a flight. And if you guys permit me, I will do it without the video.
It's okay. It's okay. You're welcome. You're welcome, doctor.
That's why he's coming.
Thank you so much. Yes. Good evening, good morning, good afternoon, ladies and gentlemen. This is a great opportunity to be here and marvelous. Thank you so much for the invitation. I guess I'm speaking for the third year here, and I'm excited to be a part of this whole speaker session. Thank you so much for the previous speaker. He's been extremely good, and this time marvelous. I should congratulate you because I think a lot of variety of speakers, and they're doing amazing. Well, with regards to Space Kids India, it's an organization that was started in the year 2010. At 15 years. Student experiential learning organization where I was taking children to NASA, ESA, and GCTC space camps, and touching the rockets and touching the satellites, just give that feel. What are the youngsters of my country doing? Probably, we need to move on to build satellites because space is the future. And if we are not bringing the youth to building satellites, then how are we going to progress? So that was a huge question, so I wanted to answer those questions and started off bringing these children from tier 2, tier 3 towns where internet was a luxury to them. And, mentoring these children, showing them the Indian Space Research Organization. Everything was a great experience and exposure. And then ultimately we started building payloads. Our first payload went up a high altitude balloon in 2015. And today, proud to say that the only organization and the only woman founder in the world to have launched 27 space missions, where we have 5 orbital missions. I'm so happy, marvelous, that I had an opportunity to meet Joshua from your team. And we did have a lot of interaction about building the drones and high altitude balloons there for Nigeria to start with in Africa. So think about Mission Shakti Sat. This is a huge culmination of, I'm sorry for the flight announcement. Well, 2 years ago, we launched a satellite built by 750 rural girls of India. You know, Kashmir to Kanyakumari, the length and breadth of India. And that puts me hard to see the impact of the girls, because we hardly have about 14 to 19% of girls in this industry globally, and just 2 to 3% of them, 2 to 3% of them in leadership roles. What does this mean? We're just going to have black jackets in a room? What about the pink jackets? Because there's a thin line between rockets and missiles. I truly believe that if the room is filled with black jackets, only black jackets, then it's going to be missiles. If the room is going to be filled partially with black and partially with pink jackets, I think it's going to be rockets for humanity. So that's why I started working for girls to bring them and give them an opportunity equally into this industry. Absolutely versatile girls are. It is just that they are always set to believe they are good with family economics, arts, culture, food, but not in deep tech. That is sad. So that is where we give them that self-belief that deep tech is for women too. Mission Shakti stands as an embodiment, an icon for peace and power to a girl child. So this is going to be a spacecraft built by 12,000 girls from 108 countries to the moon. Why moon? It's a huge question many people have. Well, if we launched a satellite to low Earth orbit, then we have to track the satellite through a mobile app or an app online. And if we launched it to the moon, any part of the world, any girl child, any time, can just feel that her peace is on that moon. And that is going to give a huge hope for all the children across the globe. So this is Mission Shakti Sabbath, where we want girls to believe that they can do it. So I think, please forgive me, people, flight is taking off. So my colleague Srikanth is in here, and he will be playing our journey video to showcase what we have done in these few years. So thank you so much for this opportunity. Malete, my son, thank you so much. And thank you, everybody. Srikanth, if you can play the video, that'll be great, just to see about our mission. Take care and see you later.
हमारे स्पेस प्रोग्राम में देश के असंख्य युवा वैज्ञानिकों का योगदान है। हम इस बात का गर्व करते हैं कि आज हमारे स्टूडेंट्स द्वारा डेवलप किए गए सैटेलाइट्स और साउंडिंग रॉकेट्स अंतरिक्ष तक पहुंच रहे हैं। इसी 24 जनवरी को हमारे विद्यार्थियों द्वारा बनाया गया कलाम सेट लॉन्च किया गया है।
बच्चों के जरिए हमने सैटेलाइट्स बना सकते हैं करके हमने दुनिया को प्रूव किया।
Wow, wow, wow. I can see some reactions. They're so good. Can I welcome now Francis to give at least some remarks about Doctor? Francis, are you frozen? Okay, seems like Francis is frozen, I think. Anyway, we'll go ahead back to Dr. Neal, but if anyone has a question for Dr. Kesan, please write your questions in the chat, and then we'll forward them to her. Now I'll share my screen for Neal to be next. Can you all see my screen? Hopefully.
Yes, it's visible.
Thank you so much for replying. So we have Neal Lachman, founding CEO of Titan Space Industries in United States. He's a serial entrepreneur and futurist whose decades-long career is defined by challenging industry conventions and pioneering breakthrough technologies. As the founding CEO and Chief of Spacecraft Design of Titan Space Industries, he is now channeling this pioneering spirit to build the critical infrastructure for a thriving CIS lunar economy. Neal has a profound legacy of technological anticipation and disruption. Starting in 1992, he spearheaded advanced initiatives in the satellite and telecom industries, securing global digital satellite broadcast licenses in 1995 and piloting a multi-hundred megabit internet downlink in 1999, years ahead of its time. He helped pioneer fiber to the home since 2000. These ventures forced global industry giants to change their strategy, effectively laying the digital foundation for the connected world we now take for granted. Today, Neal leads TSI in shaping the next great revolution space. Under his leadership, TSI is transforming the concept of CIS, lunar commerce, from speculative theory into engineered reality. The company is claiming a safe, affordable, reusable, high-frequency space access architecture, utilizing a fleet of horizontal takeoff and landing space planes. With audacious ambition, TSI aims to be the largest aerospace company in the world within 5 years, making access to Earth's orbit and the moon as routine as transcontinental flight. Neal Lachman isn't merely responding to trends, he is setting them, building the frameworks that future generations will rely on, and leading the charge into a multiplanetary era. Neal, you're welcome.
Hi, thank you. Let me see. Okay. I think I have to switch off my phone and then focus on my laptop. Yeah, that works. So, do you want me to share my screen now?
Yes, Neal, you can share your screen.
Yes? Okay, let me
Yes.
see.
Oh, people are excited. See how they're reacting.
Which one is this? Okay, yep. Yes. Do you see it now? Can you people see my screen?
No, it's not
I
visible.
can't hear.
No, I can't see it.
Can you hear me?
Yes, Neal,
I don't hear
I
you.
can
people.
hear you.
And I am sharing my screen. Can you see this?
Yes, it's visible.
Yes,
Hello?
we can see it.
My fault. I am supposed to be a hardcore technologist, but this was eluding me. My apologies. I had my ears in and I had my laptop muted. So yes, I can see my screen now. Thank you so much. I want to start first with thanking the organization, especially Marvelous. Thank you for the invitation and thank you for the guidance. I appreciate the opportunity to present something that I think is important to discuss, and it happens to be that we are working on that. So, without further ado, please allow me. I don't often present people, so my apologies. So I am enlarging my screen, so it has to yeah. So how do I do this? Oh, anyway, yeah. So this is my company. I founded this company together with some, I think, 15, 20 people 4 or 5 years ago, and we are setting out to indeed pioneering a next generation transportation system. So And I will answer. Oh, I have to go to the. My apologies, people. I have to go here, I think. I have to go to the. That's it. Okay, here we go. So this is a little bit about a company. I will answer all your questions that you have. The idea is that we build infrastructure for space tourism, space launch, and space transportation. And it should be from Earth surface all the way to the lunar surface. Now, to finance that, it will take some 10, $20 billion with a B. So we as an organization specialize in that kind of large scale concepts. Now, let's start with the most important thing, the problem. So, by the way, people, can you hear me? Can you confirm that you can hear me and that you can see this slide?
Yes,
It's on the problem.
yes,
Can you see? Okay.
yes,
Okay,
Neal,
thank you.
You're welcome.
Perfect. Thank you. So, listen, people, a few things. We have been on the moon 50 plus years ago. So it has been proven that we can do that kind of extraordinary technological feats. But we went there with a rocket. Rockets are the means of transportation and launch today. However, rocket launch technology is basically 11th century technology. The Chinese used it in the 11th century. It's basically a ballistic missile. Now, everything can be done at small scale. Rocket launch will allow us to do things at small scale. It has been going on for the last 50, 60 years, and the last 20 years in a more higher cadence. Now, the problem is when you want to build a large-scale economy, as the industry is saying, 1.8 trillion or $2+ trillion economy in space and on the moon, you will not be able to do that with rocket launches. Now, Elon Musk understood that. That's why he's working on Starship, where he says, you know what, I want to take 100 people per flight to space, even to the Mars. And he wants to have ultra heavy lift capability in the rocket. So that's the right vision. He has the wrong vehicle. Starship most likely will not work for the intended purposes that he thinks. So, long story short, in order to create a multi-trillion-dollar cislunar economy, in order to transport many people, hundreds, let alone thousands, you will need another solution. This will not happen with rocket technology. This is where we come in. We are working on the solution. The most important part of space transportation, space travel, whether it is from here to Leo and beyond, is to escape the thick atmosphere of Earth. That's why a rocket launches with so much power. It has to escape our atmosphere in order to then reach space. That's also why they use multiple stages. I hope that's clear. By the way, I will answer your questions. You can even interject here if you want. Now, the thing is, 50 years ago, the builders of the NASA Space Shuttle space planes, the orbiters, Rockwell International, and a lot of other powerful companies came up with solutions that would replace rocket launch technology. Instead, they were looking at what we call space planes, rocket ships. So you will see here at the top, the Titan space plane. That is based on 50-year-old concepts where these powerful companies and those geniuses said, we can build that space plane now. And this is 50 years ago, people. Now, it didn't happen for many reasons, but the technology was ready back then, as they said. We, Titan Space Industries and myself, we took that plan out of the freezer, and we have been developing this for the last almost 5 years. The space plane will take off like an airplane horizontally from a runway and then escape Earth's thick atmosphere with a technology that's already been used for the last 60 plus years, and that's jet engines. So commercial off-the-shelf jet engines that we modify with afterburners and ramjets to make it even more powerful, but to function in the thick atmosphere of Earth. So instead of a rocket, you will use this space plane. It has so many benefits because you can reuse this space plane hundreds of times, just like just like an airplane. It takes off just like an airplane, and it is safe. And because you can reuse it a lot of times, it is also ultra low cost. So all of a sudden, we have presented the solution to the most important and limiting and restricting aspect of space transportation, and that's the space plane. Now, from here, everything becomes easier to understand. The second that you see here is the LEO Titus Orbital Port Space Station, LEO TOPS. We say this is the future of on-orbit working and living. The ISS is at its end of life. They are going to decommission it in the next 5 years, 4 or 5 years. And a lot of commercial companies are trying to find a way into NASA's budgets. We basically don't care. We are saying we're going to build this space station with or without government contracts. Why? Because we aim at the commercial and the private market. Now, on the other hand, this technology, this space station, is based on the most advanced technologies, and basically it's the best design and the best architecture that you can find. We explained that in detail in a 130-page critical design review that we published just last week. So the space station looks futuristic. It has a beautiful look to it. But that design is not just for fashion or form or beauty. It has function. It has powerful functions that other space stations cannot. For example, it has a shield that works as a hanger that is protective of the internal structures. Now, it's a long story. You can read about that in our newsletter when you go to my LinkedIn. But that's one space station. There will be another space station. You can see that at the end, at the bottom. That's the Lunar Space Station. That Lunar Space Station is smaller than the Leo Space Station. However, to get there, cislunar, from Leo to Lunar Space Station, you need a transportation vehicle. Now, today, and as a matter of fact, in the Apollo era, 50 plus years ago, they used, of course, staged rockets, rocket stages. And the transportation method would be the modules that then orbit Earth, the moon, but that was limited to three people, 2 or 3 people usually. Now, that is indeed, again, a reference to the limitation of the technology. We have designed what we call TSOT, Tiny Spaceship Orbital Transporter, for large-scale transportation, 36 people at one time, and 50,000 kilo of payload. You can see that at the third image. So basically, this transportation system takes you from Earth's surface, from a runway, not a rocket launch pad, from a runway to a Leo space station, where you transfer on an orbital transporter to the Lunar Space Station. People, it's as simple as that. There's no magic involved, no magical engines involved. This is technology that is currently available and or developed in the next few years. I'm sure you will have some questions about this, and I'm eager to answer those questions. So here you see the space plane, the Leo space station, this orbital transporter, and the Lunar Space Station. Those 4 vehicles, those 4 spacecraft will replace any rocket system that is currently being developed. You don't need that anymore. Very simple. Now, I want to highlight the Lunar Transporter. We are working on the 3D renderings and so on. But this transporter is a simple, elegant solution for a problem that NASA paid, I believe, $7 billion for. And the solutions that they have today, whether it is Blue Origin or SpaceX, those spacecraft are very limited in the scope of operations. they will not be as efficient and as reusable and as low cost as this lunar transporter. By the way, if you have seen the series Space 1999, you will see that this has been inspired by that series. It will be the most important vehicle that lands, that takes you, ferries you to and from the lunar space station. Now, anyway, the plan, people, is to settle the moon, to colonize the moon. And this is not my idea. This idea of colonizing the moon, industrializing the moon, has been proposed for at least 60 plus years. It started being evangelized by Dr. Gerard O'Neill from Princeton. Now, as you all know, Hilton, Conrad Hilton from the Hilton group of hotels, they said, and Werner von Braun, they are on record, you can Google it, they said, let's build a resort on the moon. People, they said that 60 years ago. The person who developed the Apollo program, the technology, the Saturn V rockets, and so on, Werner von Braun, he was a proponent of, for example, a resort on the moon. Conrad Hilton, he wanted to build a resort on the moon. Gerard O'Neill, he said, let's industrialize the moon. Let's take heavy industries away from Earth and let's do it in space. And let's use the moon as a springboard, as an industrial base for what we will do at the moon and beyond. They were talking about Mars. So people, this is not me being a crazy guy, having a wild dream. This is based on concepts that have been around for decades. So this is not just a dream. However, the industry, including NASA, they have plans. They say, okay, let's build this a base on the moon. And we, as Titan Space, we say, okay, but who will build that, by the way? And when? And they say, oh, we're going to send 2 astronauts, maybe 4, and we'll have a swarm of robots. And we say, great, that's a great solution, robots, but robots will not be the end all and be all of the solutions. You need humans. This is where you see us recruiting the world's best and brightest as astronaut candidates. We are going to train people from next year onward, in the next few months starting, for work and living on the moon. So we are saying robots and remote controlled, autonomous, whatever, it will not work. It will not be the way we will colonize the moon and build a huge industry. We need dozens, hundreds, if not thousands of people working on the moon. Now, NASA has developed what they call the Artemis program, the Artemis missions, which is great. But if you Google it, if you don't know about it, Google it. If you Google it, you'll see that it is, again, very limited. Basically, because NASA's mandate is scientific research, space exploration. It's not industrialization. It's not commerce. So the Artemis mission is limited in its scope and objectives. We have said, you know what? All that we are building is for that purpose. And we have developed the Selene mission. Now, the Selene mission will allow us to build out over the next 4 or 5 years the infrastructure that will help us, A, live and work in low Earth orbit, LEO, and in cislunar space and on the lunar surface. So we specialize in infrastructure, people. This Selene, what we call the Selene mission, is our answer to the Artemis mission of NASA and its partners. This is the only way you can do things in cislunar space and beyond at a large scale. So at the end, you'll see that we have a moonbound flight plan from Earth to the moon and back. But yeah, people, that's basically it. I am willing to answer any questions you have. Thank you.
Wow,
Hello?
thank you so much, Neal. Thank you so much. That was very informative, and I think a lot of people have a lot of questions, hopefully.
Sure.
So anyone who has a question, please write them on the chat. I keep welcoming people, the ones who keep joining. We are now having Neal, who has just spoken a lot. And okay, people are writing questions. Bravo, Neal. Very clear and comprehensive explanation of the TSI mission.
Thank you.
Someone is saying, consider this my unofficial application for Chief Medical Officer.
We already have one, by the way. Sorry, Dr. Jeremy Saget.
So someone else is saying, it looks like a lot of Star Trek fans are here. They're like, as a Star Trek fan, this is exactly what I've been waiting for.
Exactly. So, by the way, to answer that a little bit, the space stations are indeed inspired by two amazing phenomena. One is indeed Star Trek Enterprise, and the second is black holes. So we wanted to honor nature and, of course, this amazing inspiration to a lot of people, Star Trek. Okay, so do you have any questions, or shall we go to the next guest?
Well, I think they will just write them on the chat, and I'm going to pin you on them. But for now, it seems like nobody's raising their hand. So
That's
we'll
okay,
just
no
go.
problem.
Yeah, so we'll just go back. We'll just go to the next speaker.
Thank you.
Okay. So the ones who are coming in, welcome again. And my name is Christine Fulgence from Tanzania. I am the moderator. And we are going to have our next speaker. Let me share my screen. So next we are going to have Rama. Is it everyone can see my screen?
Yes, you can.
Thank you. Thank you so much for replying. So Rama Murali, head of AIV at Space Inventor, A or S, is in Denmark. Rama is the head of AIV at Space Inventor, leading all assembly, integration, verification, which is the AIV, qualification, and industrialization activities for satellite production. He is a seasoned space systems leader with over 16 years of hands-on experience at premier global organizations, including Airbus Defence and Space in the UK and the Indian Space Research Organization, ISRO. Prior to his current role, he served as a system AIV manager and test preparation manager at Airbus, defining and managing integration and test activities for advanced microwave instruments and telecom payloads. During his extensive tenure at ISRO, he held multiple key positions, including program manager for satellite communication and navigation applications, project manager and systems engineer for several of India's most prestigious deep space and remote sensing missions, including the Mars Orbiter mission and the NISAR missions. Rama Murali's expertise spans the full project lifecycle, from mission formation and satellite systems design to AIV and applications development, implementation, and operations. He has significant experience managing diverse global teams and collaborating with multiple international space agencies. Applying this technical background to industry strategy, he is also pursuing a doctorate in business administration focused on the emerging commercial space ecosystem. He is a dedicated STEM ambassador and mentor, actively supporting the next generation of space professionals. Rama, you're welcome.
Thank you, Christine. Am I audible?
Yes, you are
Okay,
audible.
perfect. Thank you so much for the wonderful introduction.
You're welcome.
I will share my screen. Can you all see the screen?
Yes, Rama, I can see the
Perfect.
screen.
Thank you so much.
Yeah.
I should start thanking Marvelous for this wonderful opportunity to speak to everyone today. So thank you so much for this opportunity. And I think already wonderful introduction by Christine. So I will go ahead with my presentation. So this is a small introduction of a couple of slides about the company I represent. So Space Inventor is the company I work for as a head of AIV, assembly integration and verification. So we are expertise in small satellites of starting from 3U, 6U, all the way up to micro satellites, ranging from 10 kilos to 200 kilos. And it's being a vertically integrated company, we also support all the subsystems of the spacecraft as a modular systems. So, and so far we have served more than 600 plus modules in the orbit, and there are 15 plus satellites currently under production. And the satellites have even, we have the first geo satellite, the micro satellite went to geo, is also from Space Inventor. And there are 100 plus projects delivered and 300 plus modules in production as we speak. So that's a small introduction. And this is the different satellites so far we have realized in different scales. So coming to the topic of today, so I have chosen this topic where from mission to market, what is it for industrializing AIV for a sustainable space, new space age? So how AIV is transforming and what would be the future and how we need to scale up to be prepared for the new commercial space industry. So as an introduction, as we all know, the new space age is driven by rapid commercialization, and we are seeing the pioneering era has moved to commercialization and miniaturization, and now we are into new space and looking beyond. The path from mission specific, wherein we were more focused on building one full product with the more focus, has slightly shifting to modern space with multiple satellites, multiple products, viable market solutions. So as we see in the number of launches here, it is very clear that the custom-made government projects have moved to more modular, automated commercial endeavors. Now, what does it mean? It means the government-led pioneering missions have developed the core technologies. Yes, but advances in reliability and affordability fosters market entry, and business build market-driven products and services for space. So government-led missions have moved to demand-driven or market-driven. Now, what are the drivers for this change? So why there is a lot of commercial activities in space? What is driving it? The first and foremost is commercialization, and another thing is technology advances. Today, there is, as compared to the technologies available in 60s and 70s, the technology advancement is so immersed, and we have access to a lot of technologies, much advanced technologies today with AI and automation. Also, the sustainability is coming into picture. To stay sustainable, how do we reduce the resources used and minimize the space debris? All these things are driving the space industry today. Now, coming to my topic of assembly, integration, and verification. What does AIV stand for? So by definition, it is a systematic process of physically building a satellite or space system, connecting all the subsystems, be it power, communications, or altitude and orbit control systems or payload, and proving that it meets all the mission requirements. So why do we do that? What's the objective of this? Is basically the risk reduction. Satellites cannot be repaired, so we all know that. So we follow the philosophy of test as you fly and fly as you test. So we need to the workmanship defects should be minimized, or the quality is at most when it comes to assembly, integration, and verification. So as we see on the V curve, this is where we stand. So normally the requirements are defined by the systems team, and once the design is there, then it comes to the implementation. The implementation stage where we get all the systems in, we do a thorough inspection, we do start building the systems, connecting one by one, and checking whether every system works as defined or as required. And if there is an issue, we resolve that and move forward with the building the system to the perfection. And finally, we verify and validate the product. So when the space is moving from the mission-led era to production or commercialization era, where the AIV is, how the AIV is moving. Are we equipped from AIV point of view to handle this transformation? So today, why AIV is so important? Because AIV is where actual profit margins are either secured or destroyed, because that is where the systems are built. So during the building, if you're not building it rightly, it costs a mission. You need to rebuild from the start. So it is where the profit margins are played. Now, when it was a customized one mission, there was limited speed on the AIV. We could focus a lot, and we could build customized things specific to the mission. For example, the support equipment. If we have to build a satellite, we need something to support. Now that support system, supporting equipments and the test equipments around it was built customized to that mission. Now, moving forwards, when we have hundreds of satellites to be built, we cannot do it that way. It is no more viable. We need to look for modularity. We need to look for automation of the processes. We need to look for standardization and high throughput. So the traditional production line needs to be moved from singular to multiple smart factory kind of line. So this is where the AIV needs a transformation. Now, what is it involved in this transformation? So scaling up, we should be ready to scale up the volume productions and lower the cost, because that is where the cost comes into picture. The maintenance of the clean room, the space grade components, what we handle, and how we build the spacecraft, the processes around it, it costs a lot. And that's where the majority of the cost lies in the mission. So that needs to be controlled, and it needs to be scaled up to take care of multiple satellites in a short time. Then standardization. For example, if we are connecting two systems to each other and making them talk, in normal communication, because the systems come from different locations or different suppliers, there are possibilities that the interfaces could be different. Now, this is where we need to say that, no, it cannot work if the interfaces are different. Now it has to be standardized so that I can produce in large numbers rather than focusing on one. Now, further thing is automation and digital tools. Today, we have access to a lot of robotics equipments, AI, and whatnot, digital tools. So this is where we need to make use of available resources. So it's more from moving from a craftsmanship to manufacturing. That is what is the focus is shifting to in terms of AIV. Now, what it means that in different scenarios. So the production philosophy is shifting. Now we are looking into more like a production. So the modules needs to be modular. You designing for the AIV. Earlier systems were designed for the performance and the spec, and the modularity was not a concern. But today, when we have to use the same system for multiple missions or same modules in a different mission, so the modularity plays a role. For example, if you look at one of the Space Inventor modules here, so these are all different, like it could be a power system module, it could be an OBC, onboard controller module, or it could be a power interface module, or it could be a payload interface module. But if it has all have similar form factor. Now what it means is when the spacecraft bus changes, you can still use the same module in a different way. Like the integration, if you are building a stack of modules, the stack could be changed as per your convenience or as per the system requirements by using the same set of modules, so the production could be made faster. Then independent payload and bus integration. The payload comes normally at this last stage of the spacecraft integration. So when the payload comes, the spacecraft should have been completed most of the integration, so the payload integration becomes plug and play or close to that. That has to be independent. Otherwise, you cannot really wait for the payload to come and then start the integration from the scratch, so you lose a lot of time. And another thing is the standardization of the connectors. Normally, typically, if you see any spacecrafts or the space systems, you will see plenty of harness, the connectors running around, and different types of connectors and different types of harnesses around. But think of a scenario when you are building this satellite. If each harness is different, and then you have thousands of harness to connect between the systems, how much time it consumes to look into the harness, take it, read the label, where from which connector to which connector it goes, and connect it. Instead of imagine a scenario where all the standardized harness, more like a USB-C or a standard harness, what you see here in the bottom diagram, where all the harness have the similar standard. So you just take any harness of any standard length and you just connect, plug and play, or blind mating. That is what we should be looking at. And then testing the bottlenecks, like where do we draw the boundary for the testing? Do we need to test for acceptance? Do we need to test for the qualification? What kind of model we developed? And thermovacuum test optimization, because thermovacuum is normally a test where you don't have much flexibility to optimize the schedule because thermal cycles are takes time as defined. Now the question is, can we do multiple batch testing, or can we look at the way we do the testing instead of with some small rapid cycles, and what we can automate instead of staying next to the thermovacuum chamber and looking at how it is functioning, or keep on sending the scripts? Can we automate the whole scenario wherein it just pops up some flags in case anything comes, otherwise it just completes the testing automatically? And can we use cobots or robots today? For example, like let's say we have a scenario of testing a communication payload antenna wherein there are hundreds of it has hundreds of feeds. Now, how do you test it in real life scenario? In practically, if you are testing one by one with the probe, then it is enormous work. Instead, can you use the cobot or robot, which does all the 100 feeds testing automatically without a human intervention or even with minimal intervention? And for building the spacecraft, we end up, and can we use the tools which can record, like for example, the smart torque meters, which can record the values as we torque it, so that we don't need to revisit that, or we have the record automatically get updated. So these are all some of the things we need to start looking into, and we start improving in the AIV processes to be equipped for the future. And another thing, most of the places already we have seen or implemented or getting implemented is the MES, the manufacturing execution system, the software tools around it, the simulation tools. So today we will see most of us have challenges with multiple tools. How do we handle different tools handling in different systems? So a systems team will be using one tool, and another testing team will be using another team, another designer team will be using another tool. Now, how do we integrate all these tools and build one integrated tool taking care of end-to-end system? Now we have tools which says that before actually we design a system, we can simulate and see how it performs. Now, can we think of a tool which can actually more like a digital twin? Before actually we test it, we see that whether we can really test it that way, and then we go to the testing. In that way, moving forward, can we digitalize the testing? So this is a broad spectrum of activities which are progressing. So if you see from the bottom, it's most of the things are today functional. So we are moving outwards from the source. If you look at it, another 2 to 5 years, most of these middle blocks would have been realized. And further, there is like we are looking at into the future with fully robotic matings, in-space assembly manufacturing, or zero harness architectures, fully wireless architectures. And today in commercial, in our commercial markets, we have inductive power transfer. So can we bring in into space, or software-defined hardware interfaces, or the digital twin, as I was saying, where we test the model and fly the hardware, or self-diagnosing satellites, and autonomic scheduling and line balancing. So these are all some of the futuristic things. If we start thinking from today and start implementing what we can do best, I think we will be equipped to handle a future wherein the fully commercialized and a fully sustainable space industrial base for the space. Now, as we look into the future, this is what we see into the space outlook. So building a self-sustaining industrial base in space, a holistic integration of market needs and a sustainable practice, trends like in-space, assembly and manufacturing, autonomy, and modular satellite constellations. So what it means for further is like a lot of the discussions like space drug factory or 3D printing in space, space force or electricity from space. They all needs a futuristic AIV in place to make it reality. So, so it is important to design for reusability and in space, think of in space manufacturing and servicing and resource efficiency. So what it involves in terms of implementation strategy is in 3 points. One is design. So we should design the satellites that could easily be tested, and we should have the right infrastructure, and we should have flexibility in the infrastructure, and the culture of perfect performance at all costs to repeatable performance at scale becomes important. And being an enablers for this would be design for manufacturing and IT security infrastructure and workforce upskilling. So we need rocket scientists, but also we need process engineers to do this. So as a conclusion, industrialization of AIV enables scalable and sustainable growth in space, but the transition from mission-led to market-driven industry secures a long-term success. So we are actually moving from the era of Ferrari to a Ford Model T, wherein we are looking for reliable, mass-produced, accessible. So industrializing AIV isn't just about building faster, it's about building a sustainable future where space is accessible to all. Thank you.
Thank you so much, Rama. Such a good presentation. Can I see reactions, please? Yes. They're applauding you, Rama. You should be
Thank you.
smiling.
Thank you. Thank you so much.
Anyone who has a question before I make a quick summary? If anyone has a question, please write them on the chat.
Yeah.
So with the ones who have recently joined, I'll make a quick summary. We first had Dr. Taofiq, who just presented about the interest that he already has in the research. The research interest he already has in aerodynamics, fluid dynamics. We saw a lot of questions, and my head was almost in dizziness because of the a lot of the questions. And then next we had Dr. Srimathy, who is the founder and CEO of Space Kidz. We have seen how much she has achieved with Space Kidz. And also we had Neal, who we have seen how much work he has done to the TSI, the work they're doing. And now at the end, we just have Rama, who has spoken about the things you've seen. the robots, AI, and stuff like that, the outlook of the future if implementing steps. So the ones who have questions, please, you can just write them on the chat. We are going to have a break for 30 minutes, and then we'll be back. And right now it's now I'm in Tanzania, so my time here reads 8:58. So let's say just 21 hours. So we'll be back at 21:30 hours, which is 9:30. I don't know how. I don't know the time there. Just counts 30 minutes in whatever country you're in. After 30 minutes, we'll be back and we'll continue with the rest of the speakers.